Math 2414, Trigonometric Substitutions, Video 4, Summary for Using Sine. So in the previous videos, we did a couple of integrals, and you'll notice that the integrands contained some square roots, which are listed here. In the first example, we did an integral of the square root of 1 minus x squared. In fact, that was the entire integrand. In the second video, our integrand contained the square root of 9 minus x squared. And we're going to generalize this by replacing the left side of the subtraction problem with some generic squared number, which we're calling a squared. Let's document our trig substitutions that we used. In the first video, or the first and second, for the square root of 1 minus x squared, we said x was equal to sine of theta. In the second video, however, we used x equals 3 sine of theta, the 3 being there because of the 9 on the left side of the subtraction problem right here, and the fact that 3 squared is equal to 9, or the square root of 9 is equal to 3. So in general, when we're integrating an expression that contains, when we're integrating a function that contains the expression square root of a squared minus x squared, and we're going to use the trig substitution, x is equal to a times sine of theta. Now remember, the reason this works is that when we take this, put it here, we get a squared minus, well, if x is equal to a sine theta, then x squared is a squared sine squared theta. And what that will always do is make these coefficients match, which means that we can factor them out. You get a squared times 1 minus sine squared theta. And there's the Pythagorean identity that allows us to condense the subtraction problem to cosine squared theta. And it'll happen that way every single time. So it's all about setting it off with the correct substitution. In this case, if you're integrating something containing the square root of a squared minus x squared, then you should let x equal a sine theta. Let's try a few, not where we're integrating, but just determining the substitution. First one's easy, second one's trickier, and the third one involves something I haven't shown you yet. Let's take the square root of 25 minus x squared. By the way, it's important to point out that in these subtraction problems, the x squared is on the right side of the subtraction because the trig identity we're taking advantage of has the trig function on the right side of the subtraction. All right, so what would we use, what would we use for the square root of 25 minus x squared? Well, it's going to be a sine theta because it's minus an x squared. And then the coefficient of that is the square root of the number on the left side of the subtraction. The square root of 25, of course, is 5. If we used x equals 5 sine theta, it would collapse the subtraction problem down to a single trig function, which would also square root nicely. But what about the second one, the square root of 7 minus x squared? Well, structurally speaking, the x squared is on the right side of the subtraction problem, which means we're still going to use sine theta. But what coefficient would we use? What could we put in front of the sine theta so that when we squared it, we would get 7? Well, that's equivalent to asking what the square root of 7 is, and the square root of 7 is square root of 7. So even if the number on the left side of the subtraction is not a perfect square, this substitution will work. You just have to unsquare that number. And if you're lucky, it will unsquare cleanly, like 25 unsquares into 5. But if it's not a perfect square like 7, just slap a square root over it. What about this last one? Structurally speaking, it is the subtraction problem with an x on the right side of it, which is what we want, but obviously this has a 4 in front of it. Now, there's a couple of ways to make an accommodation for this, and when we get to the end, you'll see what it is. But let's take the same approach that we took before, which was to try to match the subtraction problem to a trig identity. Now, because the x is on the right side of the subtraction problem, the trig identity that we want to match this to is 1 minus sine squared of theta. And we can fix the 9 easily by multiplying the entire thing by 9. Can we get the 4 to match? Well, no, but that's not our biggest concern. Our biggest concern is to get the 9 to match. So if we multiply this by 9, we get 9 minus 9 sine squared theta. And remember, once we get the 9 minus matching, then we just equate these guys and figure out what x equals. Oh, let me see if I can move that over a little bit. if we're going to equate these things, then we need 4x squared equal 9 sine squared theta. Solve that for x. We would divide both sides by 4, which would get rid of the 4 in front of the x squared. And then we would square root both sides. And if we square root both sides, we get x equals 3 sine theta over 2. And that would be our substitution. And it would probably be cleaner to write it as 3/2 sine theta. But again, the motivation for this is to connect the subtraction problem to a trig identity that has a constant in the correct place and a variable in the correct place. Because the constant is on the left of the subtraction problem and the variable is on the right, the trig identity, or rather the expression inside of a trig identity that we're trying to connect it to, is 1 minus sine squared theta. So let's just go ahead and clean this up and write our substitution. X is equal to 3/2. Ahead of myself there. 3/2 sine theta. And as you can imagine, it's probably not that difficult to generalize the case where not only do we have a constant on the left side of the subtraction, but we also have a constant in front of the x squared. Let's put this in green because I like green. If we had something like the square root of a squared minus b squared x squared, and the reason I'm writing the b as a square is because I'm going to square root it just like the square root of 4 became 2 there. But if we had something like that, then we could say that x is equal to a over b sine theta. And if you want to memorize that as opposed to number 3 here, that's fine. I can't stress enough that memorization is nothing you don't understand. Because memorization only allows you to do a certain caliber of problem. Understanding allows you to